I'm Aureliane from Quebec. Bonjour! Do you think bacteria are always the bad guy in a story? They can be deadly for sure, but they can also be quite helpful and fun. Let me tell you a story about my friend here, a cherry chocolat, say hi colleague, and how it can glow in the dark. For years now, we have heard about bacteria becoming resistant to antibiotics and that we are running out of solutions. And it's true, sadly. As soon as a new molecule is discovered, the bacteria quickly find a parrot to get resistant. We are basically training them to become stronger. It's an arms race and we are losing it. One of the reasons for that is quite simple. We don't know our opponents very well. It has just one side of the coin. Bacteria can also be quite useful to produce molecules for us in medicine or industry. We can use them to detect molecules involved in disease, like cancer, or even pollutants in the environment. In any case, we need to know more about those guys' metabolism first. Because we all know how sci-fi characters end up when they use tools they don't really understand. So, how do we do that? Well, we use riboswitches. Colai, do you know what a riboswitch is? No? Let me explain it to you. A riboswitch is a structure present just before some genes in the bacteria genome that works as a switch to turn the gene expression on or off. Naturally, those riboswitches are used to help the bacteria adapt to its environment, enhance survival, and potentially its pathogenicity. The trigger for that switch is a tiny molecule, usually linked to the regulated gene. In our case, when the molecule is present in the bacteria, the riboswitch turns the gene expression off. I imagined a detection system on a mobile DNA called the plasmid, where I put the riboswitch in front of a fluorescent protein. That way, when the molecule is present inside the bacteria, the riboswitch turns the fluorescent off. I prepared different switches and then I cut the plasmid with molecular scissors called restriction enzymes. I inserted the riboswitch and the fluorescent protein and glued everything back together. The detector is now ready and needs to be put into the bacteria, our dear E. coli. After the procedure and the bacteria recovery, the fun begins. I incubated these bacteria equipped with the fluorescent detector in different growth conditions. At first, the addition of the trigger molecule didn't change much of the fluorescence intensity. But after a few optimization steps, I have now a good detector for thymine pyrophosphate, TPP for short, which is a molecule quite important in the metabolism of the cell. The detector can tell us about the presence of TPP as well as its concentration inside the bacteria. It is cool by itself, right? But wait, there's more. In the lab, we have a collection of 4,000 individual mutant strains for every gene of E. coli that is not essential for its survival. Every single one of them is deleted, one at a time. I put the detector in them and watch what happened compared to the regular bacteria with all of its genes intact. If the bacteria glows brighter, there is less TPP in it. But when it goes fainter, TPP is more abundant. Now, I am currently in the detective work, where I am trying to understand why some genes that are at first completely unrelated to TPP still impact its concentration inside the bacteria. This will potentially lead us to the discovery of new metabolic pathways, because even if E. coli is the most studied bacteria in the whole world, there is still a lot of we don't understand. But this is just the beginning of the story, of the adventure even. Here I told you the story of the TPP riboswitch, but there are dozens of different ones in nature. We can even create our own to detect artificial molecules of interest for medicine of industry. From there, sky is the limit. So, are you ready for an encounter of the third kind with tiny green creatures?